Hello there, and welcome to the Sleepy Library, where we explore the wonders of science in the most gentle, soothing way possible. Tonight, we are venturing beyond our blue planet, beyond the atmosphere that cradles us, to ask one of humanity's oldest questions. Is it possible for humans to live outside planet Earth? This is not a question born from restlessness alone. It emerges from curiosity, from the part of us that looks up at the night sky and wonders what lies beyond. For thousands of years, we have been dreamers, storytellers, stargazers. We have imagined other worlds, other homes among the stars. And now, after decades of technological advancement, after sending machines to distant planets and humans to orbit, we stand at the threshold of making those dreams tangible. So settle in. Let your breathing slow. As we explore the possibilities and challenges of living beyond Earth, let the information wash over you like gentle waves. There is no test tomorrow, no urgent need to remember every detail. This is simply a journey through one of humanity's grandest aspirations, told in a way that invites rest rather than anxiety. The story of humans looking toward the stars is as old as consciousness itself. Our ancestors gazed upward at the same sky we see today, though they understood it differently. They saw patterns in the stars, creating constellations that told stories of heroes and monsters, gods and legends. They watched the planets wander across the celestial sphere, noting their movements with remarkable precision, despite lacking telescopes or modern instruments. They observed the phases of the moon, the rising and setting of stars with the seasons, the occasional appearance of comets that would spark wonder and sometimes fear. These early astronomers did not yet dream of traveling to these distant lights. The heavens seemed utterly separate from the earthly realm, a domain of the divine rather than a place that could be physically reached. Yet, even then, stories emerged of journeys to the moon or stars. Ancient Greek writers like Lucian of Samosata penned fantastical tales of moon voyages. These were understood as fiction, as thought experiments, but they planted seeds of imagination that would germinate across centuries. The scientific revolution transformed our understanding of the cosmos. When Galileo turned his telescope skyward in 1609, he saw mountains on the moon, moons orbiting Jupiter, and realized that these were worlds, physical places with geography and substance. This revelation fundamentally altered humanity's relationship with the heavens. If the moon was a world with mountains and valleys, could it not theoretically be visited? If Jupiter had moons, did other stars have planets? The universe began to seem less like a divine ceiling and more like a vast expanse of real, physical locations. As centuries passed, writers like Jules Verne and H.G. Wells imagined space travel with increasing detail and scientific rigor. Verne's 1865 novel, From the Earth to the Moon, described a journey launched by a giant cannon, a method that would not work in reality, but showed serious thought about the mechanics of space travel. These stories captured the public imagination and inspired young people who would grow up to become the rocket scientists and engineers of the 20th century. The 20th century transformed space travel from fantasy to reality with remarkable speed. The development of liquid fuel rockets by pioneers like Robert Goddard in America and Hermann Oberth in Germany provided the basic technology. The pressures of World War II accelerated rocket development dramatically as nations sought long-range weapons. After the war, those same rocket technologies were adapted for peaceful exploration. The space age truly began on October 4, 1957, when the Soviet Union launched Sputnik 1, the first artificial satellite. This small metal sphere, about the size of a beach ball, orbited Earth for 3 months, transmitting a simple radio beep that anyone with the right equipment could hear. That beep announced a new era. Humans had succeeded in placing an object beyond Earth's atmosphere. The pace of achievement accelerated rapidly. Within 4 years, Yuri Gagarin became the first human in space, completing a single orbit of Earth on April 12, 1961. Less than a month later, Alan Shepard became the first American in space. The race was on. Both superpowers poured enormous resources into space programs, driven by Cold War competition, but also by genuine scientific curiosity and the ancient human drive to explore. And then, on July 20, 1969, something extraordinary happened. Neil Armstrong and Buzz Aldrin walked on the moon. They spent just over 2 hours on the surface, collecting rocks, taking photographs, and planting an American flag. But those 2 hours represented the culmination of millennia of dreaming and decades of intensive work. Humans had left their planet and stood on another world. 5 more Apollo missions successfully landed on the moon through 1972. 12 humans in total walked on the lunar surface. They explored different regions, collected hundreds of pounds of rock samples, conducted scientific experiments, and demonstrated that humans could function in the lunar environment. Then the Apollo program ended, and no human has returned to the moon since. Why did we stop? The reasons were complex, involving political changes, shifting priorities, and the enormous cost of the program. Once the goal of beating the Soviet Union to the moon was achieved, public and political support waned. The Vietnam War and domestic social programs demanded resources. The space program continued, but focused on different objectives: space stations, planetary probes, and the Space Shuttle program. Yet the dream of returning to the moon and venturing beyond never faded. It persisted in the minds of scientists, engineers, and space enthusiasts. And now, more than 50 years after the last Apollo mission, we are on the cusp of a new era of space exploration and settlement. This time, the goals are more ambitious and the timeline potentially much longer. We are not just planning to visit other worlds, but to stay. Let us begin with the most fundamental question. Why would we even consider leaving Earth? Our planet is beautiful beyond measure. It is a world of blue oceans that shimmer under sunlight, reflecting clouds that drift across azure skies. Green forests stretch across continents, teeming with life in forms too numerous to count. Rivers carve through landscapes, providing water and habitat. Mountains rise toward the heavens, their peaks crowned with snow. Deserts spread their golden sands under brilliant sun. The air is filled with oxygen, perfectly suited for our lungs. Temperatures across much of the planet remain within comfortable ranges for human life. Earth has everything we need: abundant water, fertile soil for growing food, materials for shelter, and a protective magnetic field that shields us from harmful radiation streaming from the sun and distant stars. Earth is, by every measure, the perfect home for human beings. We evolved here over millions of years, shaped by this environment, adapted to these precise conditions. Every aspect of our biology reflects Earth's influence. Our eyes are tuned to the wavelengths of light that penetrate our atmosphere. Our inner ears balance us in Earth's specific gravitational field. Our circadian rhythms match the 24-hour rotation of our planet. We are children of Earth in the most literal sense. And yet, there are compelling reasons to look beyond this perfect home. These reasons range from the practical to the philosophical, from immediate concerns to visions spanning millennia. The first reason is survival, plain and simple. Earth, despite its beauty and seemingly permanent nature, is vulnerable in ways that become obvious when we examine our planet's history. The geological record reveals that mass extinctions have occurred multiple times. The most famous occurred 66 million years ago, when an asteroid approximately 6 miles in diameter struck what is now the Yucatan Peninsula in Mexico. The impact released energy equivalent to billions of nuclear weapons. Dust and debris thrown into the atmosphere blocked sunlight for months or years, causing global temperatures to plummet. Plants withered and ceased photosynthesis. Food chains collapsed from the bottom up. 3/4 of all species on Earth vanished, including the non-avian dinosaurs that had dominated terrestrial ecosystems for more than 160 million years. This was not the only mass extinction. Scientists have identified at least 5 major extinction events in Earth's history, each eliminating the majority of species alive at the time. The causes varied. Asteroid impacts, massive volcanic eruptions, sudden climate changes, atmospheric composition shifts. The Permian-Triassic extinction event, which occurred around 252 million years ago, was even more severe than the one that ended the dinosaurs. It eliminated roughly 96% of all marine species and 70% of terrestrial vertebrate species. Life on Earth came perilously close to complete annihilation. These catastrophes are not merely ancient history. They could happen again. Astronomers have identified numerous asteroids whose orbits bring them close to Earth. Most are small enough that they would burn up in the atmosphere or cause only localized damage if they struck the surface. But some are large enough to cause global catastrophe. Space agencies around the world monitor these near-Earth objects carefully, tracking their trajectories and assessing the risk they pose. While the probability of a major impact in any given year is extremely low, over geological timescales, such impacts are inevitable. Beyond asteroid impacts, other natural catastrophes threaten. Supervolcano eruptions, like those that have occurred at Yellowstone in the distant past, could blanket large portions of the planet in ash and trigger volcanic winters lasting years. Solar storms could damage electrical grids and satellite systems that modern civilization depends upon. Nearby supernova explosions, though rare, could bathe Earth in harmful radiation. Gamma-ray bursts from distant cosmic events, if aimed at Earth, could strip away our ozone layer and expose the surface to deadly ultraviolet light. And then there are the threats of our own making. Nuclear war, though less likely now than during the Cold War, remains possible. Climate change, caused by human greenhouse gas emissions, is already altering weather patterns and sea levels. Pandemics, whether natural or engineered, could spread globally with devastating speed. Artificial intelligence, if developed without proper safeguards, might pose existential risks. Nanotechnology and biotechnology offer tremendous benefits, but also potential dangers. The point is not to induce fear or anxiety as you lie here listening. Rather, it is simply to acknowledge reality. Earth, wonderful as it is, does not guarantee our species' survival indefinitely. By establishing human presence on other worlds, we create insurance against planetary catastrophe. If something were to render Earth uninhabitable or severely damage human civilization here, communities on the Moon, Mars, or in space habitats could preserve humanity and our cultural heritage. They could potentially even help Earth recover, sending resources and knowledge back to aid in reconstruction. This is sometimes called the backup Earth rationale for space settlement. Physicist Stephen Hawking was a prominent advocate of this view. He argued that humanity's long-term survival requires us to become a multi-planetary species. In his words, Keeping all our eggs in one planetary basket is too risky, given the numerous threats we face. The second major reason for space settlement is resources. Modern civilization depends on materials that are becoming increasingly scarce on Earth. Consider platinum group metals, which include platinum, palladium, rhodium, iridium, osmium, and ruthenium. These elements are essential for catalytic converters in vehicles, which reduce harmful emissions. They are used in electronics, medical devices, and chemical processing. They have applications in fuel cells that might power a clean energy future. Yet these metals are extremely rare on Earth's surface. The reason for their rarity relates to Earth's geological history. When our planet formed from the solar nebula about 4.5 billion years ago, it was molten. Heavy metals like iron, nickel, gold, and the platinum group metals sank toward the core. This left the Earth's crust depleted of these valuable elements. The metals we mine today came later, delivered by asteroid impacts after the planet had cooled and developed a solid crust. Essentially, we are mining the remnants of ancient asteroid strikes. But asteroids themselves contain these metals in much higher concentrations. Some asteroids are thought to be fragments of differentiated planetesimals, small planets that formed early in the solar system's history and then shattered in collisions. The metallic cores of these ancient worlds became M-type asteroids, composed primarily of iron, nickel, and precious metals. A single, medium-sized metallic asteroid might contain more platinum group metals than have ever been mined in all of human history. The same is true for rare earth elements, a group of 17 metals essential for modern electronics, magnets, and renewable energy technology. These elements are not actually rare in an absolute sense, but they are difficult and environmentally damaging to extract from Earth's crust. Meanwhile, they exist in more accessible forms on the Moon and in asteroids. Water, surprisingly, is another valuable space resource. While Earth has abundant water, launching it into space is enormously expensive. A single kilogram of water costs thousands of dollars to lift into low Earth orbit. Yet water is essential for space activities. Humans need it for drinking, growing food, and hygiene. More importantly, water can be broken down into hydrogen and oxygen, the components of rocket fuel. Having water sources in space, particularly on the Moon or in near-Earth asteroids, would revolutionize space operations by making it possible to refuel spacecraft without launching all the propellant from Earth. Research has confirmed that water ice exists in permanently shadowed craters near the lunar poles, in subsurface deposits on Mars, and likely in many asteroids, particularly carbonaceous chondrites. Learning to extract and process this water would be a game-changing capability for space, exploration, and settlement. The third reason for venturing beyond Earth is more intangible, but no less important: the human drive to explore. This is hardwired into our nature by evolution. Our ancestors, who stayed in familiar territory, faced competition for limited resources. Those who ventured into new lands found new opportunities. The ones who explored, who risked the unknown, who crossed rivers and mountains and seas, often thrived. They found new hunting grounds, new sources of food and materials, new places to raise their children. Over countless generations, this selected for curiosity, for wanderlust, for the willingness to take calculated risks in pursuit of discovery. This drive has shaped human history. Our species originated in Africa, but within a few 100,000 years of our appearance, we had spread across that continent and begun moving beyond it. By 50,000 years ago, humans had reached Australia, crossing significant stretches of ocean to get there. By 15,000 years ago, we had populated the Americas, having crossed from Asia either by land bridge or by coastal migrations. By 1,000 years ago, Polynesian navigators had settled islands scattered across the vast Pacific Ocean, using their knowledge of stars, currents, and bird behavior to find tiny specks of land in an enormous sea. We have always been explorers. We climbed Mount Everest because it was there, as climber George Mallory famously said. We descended to the deepest point in the ocean, the Challenger Deep in the Mariana Trench, nearly 7 miles beneath the surface. We ventured to the North and South Poles, enduring extreme conditions to reach these goals. And we looked up at space and said, that too, we must go there as well. This drive is not merely about adventure or thrill-seeking. It is about expanding the sphere of human knowledge and capability. Every new environment we explore teaches us something about the universe and about ourselves. Every challenge we overcome makes us more capable, more resilient, more creative. The technologies developed to meet these challenges often find applications back home, improving life on Earth in unexpected ways. The space program has already given us countless innovations: satellite communications, GPS navigation, weather forecasting, medical imaging techniques, water purification systems, solar panels, computer miniaturization, and much more. The act of reaching for ambitious goals drives innovation in ways that more modest aims cannot match. The fourth reason is vision, the long-term perspective that looks beyond our individual lives, and even beyond our civilization's current form. If humanity remains confined to Earth, our long-term prospects are limited by the lifespan of our planet's habitability. Earth will not remain hospitable forever. The sun is gradually brightening as it ages. In roughly 1 billion years, this increased solar output will cause Earth's oceans to evaporate. In about 5 billion years, the sun will expand into a red giant, potentially engulfing Earth entirely, or at least rendering it molten and uninhabitable. These timescales are almost incomprehensibly vast. 1 billion years is more than twice as long as complex life has existed on Earth. 5 billion years is longer than our planet has existed so far. It seems absurd to worry about such distant events. And yet, if we think in terms of species survival, these timescales become relevant. Many species have existed for tens of millions of years. If humanity survives even a fraction of that time, we will need to address the question of what happens when Earth becomes uninhabitable. By becoming a spacefaring civilization now, we lay the groundwork for a far more secure long-term future. A civilization spread across multiple worlds and space habitats could persist for as long as the universe remains hospitable to life. We would not be dependent on any single location, or even any single star system. This is the ultimate insurance policy, purchased not for ourselves, but for generations, thousands or millions of years in the future. There is also something philosophically and spiritually significant about expanding beyond our birth world. We are the universe becoming aware of itself, capable of understanding our own origins in the Big Bang and the evolution of stars and galaxies. We are matter organized in such complex patterns that we can think, feel, create, and love. The emergence of consciousness and intelligence seems like a rare and precious thing in the cosmos. By spreading beyond Earth, we increase the chances that consciousness persists, that the universe continues to have beings within it, capable of appreciating its beauty and understanding its workings. These are the reasons why scientists, engineers, entrepreneurs, and visionaries have devoted their lives to answering the question, can humans live beyond Earth? And the answer, based on current research and technological development, is a cautious yes. It is possible. The laws of physics do not forbid it. The technology either exists or is plausibly achievable. The resources are available in space. What remains is the will, the investment, and the time to make it happen. But it will not be easy. The challenges are numerous and severe, as we shall explore. Let us first consider the places where humans might live, beginning with the closest and most familiar, our moon. The moon has been humanity's companion since before our species existed. It has hung in Earth's sky for over 4 billion years, formed when a Mars-sized object collided with the early Earth, sending debris into orbit that coalesced into our satellite. The moon has shaped Earth in fundamental ways. Its gravitational pull creates the tides that rise and fall in Earth's oceans twice daily. These tides influence the evolution of early life, creating intertidal zones that some scientists believe were crucial for life's transition from sea to land. The moon also stabilizes Earth's axial tilt, preventing wild climate swings that might have made complex life's evolution much more difficult. Our ancestors watched the moon wax and wane through its 29.5-day cycle, using it to mark time before calendars existed. They noticed that lunar cycles correlated with tides and possibly with biological rhythms in various organisms. The moon featured prominently in mythology and religion across cultures. It was a goddess in many traditions, a god in others, or sometimes both, depending on the cultural context. Its changeable nature inspired stories of transformation and cycles. The moon is just over 238,000 miles from Earth on average, though this distance varies because the lunar orbit is elliptical rather than perfectly circular. At its closest approach, called perigee, the moon comes within about 225,000 miles. At its farthest point, apogee, it retreats to around 251,000 miles. This variation in distance causes the apparent size of the moon in our sky to change slightly, giving us the phenomenon of supermoons, when a full moon coincides with perigee. This proximity makes the moon uniquely accessible. During the Apollo program, it took just 3 days for spacecraft to travel from Earth to lunar orbit. Communication with the moon involves a round-trip light time delay of only about 2.5 seconds. If an emergency arose at a lunar base, Earth could provide guidance and support almost in real time. Compared to Mars, where communication delays range from 8 to 48 minutes round trip, the moon offers the comfort of near-instant connection with home. The moon itself is a world of stark contrasts and alien beauty. It is smaller than Earth, with a diameter of about 2,160 miles, roughly 1/4 of Earth's diameter. Its surface area is about the same as the combined area of Asia, Europe, and Australia. While this seems substantial, remember that the moon's lack of oceans means its entire surface is land, providing more territory for potential settlement than Earth's continental areas alone. The lunar surface is divided into 2 major types of terrain. The bright highlands, or terrae, are ancient, heavily cratered regions composed primarily of anorthosite, a rock rich in calcium and aluminum. These highlands cover about 83% of the lunar surface and represent the moon's original crust, formed over 4 billion years ago when the young moon's surface was an ocean of molten rock. The darker maria, Latin for seas, are vast plains of solidified lava that filled large impact basins between 3 and 1 billion years ago. These maria cover about 16% of the surface, mostly on the side of the moon that faces Earth. The moon has no atmosphere to speak of. The pressure at the lunar surface is approximately 100 trillion times less than Earth's atmospheric pressure at sea level. For practical purposes, the Moon exists in vacuum. This has profound implications. Without an atmosphere, there is no weather, no wind, no rain. Sound cannot travel because there is no medium to carry it. The sky is always black, even during daytime, because there are no air molecules to scatter sunlight and create the blue sky we are familiar with on Earth. The lack of atmosphere also means no protection from radiation or micrometeorites. Solar radiation, including ultraviolet light and charged particles from the solar wind, strikes the lunar surface unfiltered. Cosmic rays from exploding stars in distant parts of the galaxy penetrate to the surface without hindrance. Tiny meteoroids, some no larger than grains of sand, constantly bombard the Moon at speeds of many miles per second. On Earth, these would burn up as shooting stars in the upper atmosphere. On the Moon, they strike the surface, gradually eroding rocks and creating the fine dust that covers everything. This lunar dust, called regolith, is unlike any soil on Earth. It was not created by water and wind erosion, but by billions of years of meteorite impacts. Each impact shatters rock and melts some material, creating tiny glass beads. The result is a layer of fine, sharp-edged particles that ranges from several meters to dozens of meters deep. This dust is abrasive enough to damage spacesuit fabric and equipment seals. It is electrostatically charged by solar radiation, causing it to stick to everything. It is also suspected to be mildly toxic if inhaled, though the Apollo astronauts' brief exposures did not cause obvious health problems. Temperature on the Moon varies wildly. Unlike Earth, where the atmosphere and oceans moderate temperature, the Moon's surface experiences extremes. In direct sunlight near the equator, temperatures can reach 127 degrees Celsius, hot enough to boil water. In shadow, or during the 2-week-long lunar night, temperatures plummet to negative 173 degrees Celsius, cold enough to freeze carbon dioxide. At the poles, permanently shadowed craters reach temperatures below negative 220 degrees Celsius, among the coldest places in the solar system. Yet, despite these harsh conditions, the Moon has assets that make it attractive for settlement. The most important is water. For decades, scientists debated whether water existed on the Moon. The Apollo samples were bone dry, and the prevailing view was that the Moon was utterly desiccated. However, in the 1990s and 2000s, various missions found evidence of water ice in permanently shadowed regions near the lunar poles. These craters never see sunlight, remaining cold enough that ice, once deposited there by comets or produced by chemical reactions, would remain stable for billions of years. The Lunar Reconnaissance Orbiter, NASA's robotic spacecraft that has been mapping the Moon since 2009, confirmed the presence of water ice in multiple polar craters. The L-Cross mission deliberately crashed a spent rocket stage into a polar crater and analyzed the debris plume, detecting significant amounts of water. More recent observations suggest that water might exist more widely across the lunar surface than previously thought, possibly bound in minerals or as frost in shadowed regions, even away from the poles. This water is precious beyond measure for lunar settlement. It can be extracted through various methods, then melted and purified for drinking and agriculture. It can be electrolyzed, using electricity to split water molecules into hydrogen and oxygen gases. The oxygen can be breathed. Both gases can be stored and later recombined in fuel cells to produce electricity and water again, creating an energy storage system. Or they can be used as rocket propellant. Liquid hydrogen and liquid oxygen are one of the most efficient chemical rocket fuel combinations known. A lunar base that can produce rocket fuel from local water ice could support missions throughout the inner solar system without needing to launch all fuel from Earth. The Moon also has abundant aluminum, silicon, titanium, iron, and other metals in its rocks. These can be extracted through various industrial processes. Aluminum and titanium are particularly valuable for construction in space because they are strong yet lightweight. Silicon can be refined into glass for windows and habitat structures, or into solar cells for power generation. Iron can be smelted into steel for structural elements. Oxygen, essential for life, is also abundant on the Moon, but locked in metal oxides in the rocks. Various chemical and electrochemical processes can extract this oxygen. One promising method involves heating lunar regolith with hydrogen, producing water vapor that can then be condensed and electrolyzed. Another approach uses molten salt electrolysis to directly extract oxygen and metals simultaneously. These processes require energy, but the Moon offers abundant solar power potential, at least in certain locations. The lunar poles are particularly interesting for settlement. Near the poles, certain elevated areas receive sunlight for most or even all of the lunar year, making them ideal for solar power installations. These peaks of eternal light, as they are sometimes called, are rare, but have been identified through careful analysis of lunar topography. Meanwhile, nearby permanently shadowed craters contain water ice reserves. A base positioned between these two types of terrain could have both continuous power and access to water, two of the most critical resources. Gravity on the Moon is approximately 1/6 that of Earth. A person who weighs 180 pounds on Earth would weigh only 30 pounds on the Moon. This has both advantages and disadvantages. The low gravity makes it easier to move heavy objects and launch rockets. It also enables impressive feats, like the hopping locomotion Apollo astronauts demonstrated. However, the long-term health effects of lunar gravity are unknown. We know that microgravity in Earth orbit causes significant problems with bone density, muscle mass, and cardiovascular function. Will lunar gravity be sufficient to prevent these problems, or will lunar settlers gradually weaken? This remains one of the most important unknowns about long-term lunar habitation. Despite these challenges, lunar settlement is actively being pursued by multiple space agencies and commercial companies. NASA's Artemis program represents the most concrete near-term plans. Artemis aims to return humans to the Moon and establish a sustainable presence there. The program builds on decades of robotic exploration and will utilize new technologies, including the Space Launch System, a powerful heavy-lift rocket, and the Orion spacecraft for crew transport. The Artemis architecture includes the Lunar Gateway, a small space station that will orbit the Moon rather than sitting on its surface. The Gateway will serve as a staging point for surface missions, a research platform for studying the effects of deep space radiation on humans, and potentially as a waypoint for missions to Mars. Astronauts would travel from Earth to the Gateway in Orion spacecraft, then transfer to a human landing system that would take them down to the lunar surface. The landing site for Artemis missions will be near the Moon's south pole, selected specifically because of the water ice resources and potential for solar power discussed earlier. Initial missions will be short, lasting only about a week on the surface, but the program envisions progressively longer stays, eventually leading to continuous habitation. The Artemis base camp is the planned surface infrastructure. It will initially consist of the human landing system itself, which will serve as temporary habitat and living space. Astronauts will venture out in modern spacesuits to conduct geology, collect samples, test equipment, and begin prospecting for resources. They will deploy scientific instruments to study the Moon's interior structure, test radiation protection technologies, and conduct astronomy from the lunar surface where there is no atmosphere to interfere with observations. As the program develops, a dedicated surface habitat will be landed. This habitat is currently envisioned as a combination of rigid structures and potentially inflatable modules that can provide more volume for their mass. The habitat will need to provide life support, sleeping quarters for crew, a laboratory for analyzing samples, storage for equipment and supplies, an exercise area to help astronauts maintain health, and common areas for meals and recreation. It will be covered with lunar regolith for radiation protection, likely using bulldozer-like robots to pile soil several meters deep over the structure. Power will come initially from solar panels deployed on the surface. As the base expands, additional power sources might be added, including nuclear fission reactors specifically designed for space applications. These small modular reactors would provide continuous baseline power, regardless of whether the sun is shining. And they would be especially valuable during the 2-week lunar night. Transportation on the lunar surface will be essential for an expanding base. 2 types of vehicles are planned. The first is an unpressurized lunar terrain vehicle, essentially an open rover that astronauts can drive while wearing spacesuits. This vehicle will be larger and more capable than the rovers used during Apollo missions. It will need to travel at least 12 miles from base, allowing exploration of a wide area. It will carry scientific instruments, sample collection equipment, and emergency supplies. The vehicle might also be able to operate autonomously or be controlled remotely from Earth, conducting missions even when no crew is present. The second type is a pressurized rover, essentially a mobile habitat. This vehicle will have a shirt-sleeve environment inside, allowing astronauts to work in normal clothing during long journeys across the lunar surface. When they need to go outside to collect samples or deploy equipment, they will don spacesuits and use an airlock. The pressurized rover will extend the range of exploration dramatically, potentially allowing trips lasting days or even weeks. Such a vehicle could explore regions far from the base, setting up temporary camps and conducting detailed geological surveys. These rovers will need to navigate challenging terrain. The moon's surface is covered not just with dust, but also with boulders, impact craters of all sizes, and steep slopes. Some areas have been identified as lava tube skylights, openings where underground tunnels are partially collapsed. These lava tubes, formed billions of years ago when molten rock flowed beneath the surface, could provide natural shelter for future habitats. They would offer protection from radiation, micrometeorites, and temperature extremes. Exploring and potentially utilizing these caves will be one of the goals of surface operations. As the lunar base grows over the years and decades, it will require expanded infrastructure. Additional habitat modules will be landed and connected together, creating more living space, more laboratories, and specialized facilities. Greenhouses will be established to grow fresh food, providing not just nutrition, but psychological benefits from seeing living plants and having access to fresh vegetables. These greenhouses will likely use aeroponics or hydroponics, methods of growing plants without soil. The plant's roots will be misted with nutrient solution or suspended in nutrient water. This is more mass-efficient than traditional agriculture and allows precise control over what the plants receive. Manufacturing capabilities develop gradually. Initially, everything will be brought from Earth, but over time, the base will acquire the ability to make things locally. 3-dimensional printers that can use lunar regolith as raw material will fabricate simple tools, replacement parts, and even structural components. Metallurgy facilities will extract and refine metals from lunar rocks. Chemical processing plants will produce various useful substances from raw materials. The goal is to approach self-sufficiency, reducing dependence on expensive supply missions from Earth. Energy storage will be crucial, especially for surviving the 2-week lunar night. Large battery arrays will be needed to store the electricity generated during the day. Alternatively, or additionally, fuel cells could store energy in the form of hydrogen and oxygen, which are combined to produce electricity and water when needed. Long cables might even connect the base to solar arrays positioned on the peaks of eternal light, providing continuous power. Communications infrastructure will expand beyond simple radio links. High-bandwidth connections to Earth will enable video conferences, virtual reality experiences, and remote operation of equipment. A network of satellites in lunar orbit will provide continuous coverage, as no single satellite can see both sides of the Moon simultaneously. These satellites might also include navigation systems similar to GPS, allowing precise positioning anywhere on or near the Moon. Scientific research will be a major activity at any lunar base. The Moon preserves a record of the early solar system, largely erased from Earth's active surface. The ancient highlands contain rocks over 4 billion years old. Impact craters reveal materials from deep below the surface. Studying these could answer fundamental questions about how the Earth-Moon system formed and evolved. The Moon also provides an excellent platform for astronomy. Without an atmosphere to blur and absorb light, telescopes on the lunar surface could achieve extraordinary clarity. Radio telescopes on the far side of the Moon would be shielded from all human-made radio interference from Earth, allowing detection of faint signals from the early universe. The far side of the Moon, which never faces Earth due to tidal locking, is particularly intriguing. It is more heavily cratered than the near side and has thicker crust. Some of the largest and oldest impact basins in the solar system exist there. Establishing a research station on the far side would be challenging because direct communication with Earth is impossible, requiring relay satellites at the Earth-Moon Lagrange points. But the scientific returns could be extraordinary. The timeline for lunar development stretches across decades. Artemis 3, potentially launching in the late 2020s, will be the first crewed landing. A series of missions over the following years will each build on the previous one's accomplishments. By the mid to late 2030s, the Artemis base camp should be operational, capable of hosting crews for weeks or months. By the 2040s, continuous habitation might be achieved, with crews rotating, but the base never being completely abandoned. By the 2050s, a more substantial settlement with dozens of inhabitants might exist, complete with the infrastructure described above. International cooperation will likely play a significant role. NASA is working with the European Space Agency, the Japan Aerospace Exploration Agency, the Canadian Space Agency, and other partners on Artemis. China and Russia have announced plans for their own lunar base, the International Lunar Research Station, potentially open to other nations joining. Commercial companies are also getting involved, developing landers, rovers, and other systems that could support lunar operations. The economic model for lunar settlement remains uncertain. Initial efforts will be funded by governments pursuing scientific and strategic objectives. But for settlement to become truly sustainable, economic value must be created. This might come from several sources. Scientific research and technology development are valuable in themselves, though they do not directly generate revenue. Space tourism could eventually bring wealthy visitors to the Moon, providing income. Mining operations might extract valuable materials, though whether lunar resources can profitably be returned to Earth remains debatable. More likely, lunar resources would be used in space, supporting operations in Earth orbit and missions to Mars and beyond. Water from the Moon, converted to rocket fuel, might enable a cislunar economy where spacecraft refuel at lunar orbit rather than carrying all propellant from Earth's surface. There is also the possibility that the Moon could serve as a manufacturing center for large space structures. Solar power satellites, enormous arrays that collect sunlight in space and beam power down to Earth, have been proposed as a way to provide clean energy. Building these in space from lunar materials would be far cheaper than launching all the material from Earth. Similarly, large space habitats might be constructed from lunar resources. The lower gravity of the Moon compared to Earth makes it much easier to launch materials from the lunar surface to lunar orbit and beyond. Let us pause for a moment in our exploration and simply breathe. The Moon, that familiar friend that has watched over Earth for billions of years, may soon host human communities. People will live and work under that grey sky, seeing Earth rise and set over the lunar horizon. Children might grow up learning to walk in 1/6 gravity, their bodies adapting to conditions no human has experienced for more than a few days. The ancient surface, undisturbed for billions of years except by meteorites, will bear the marks of human presence, footprints that might last for millions of years in the absence of wind or weather. Habitats nestled in craters or buried under regolith, the tracks of rovers crisscrossing the dust. It is a strange and wonderful thought. Humanity, taking its first steps toward becoming a spacefaring species, establishing a foothold on the nearest world. The Moon will be our proving ground, the place where we learn how to live beyond Earth before venturing to more distant destinations. From the Moon, let us turn our attention to Mars, the red planet that has captivated human imagination for centuries. Mars shines in Earth's night sky as a reddish star, distinctly colored compared to the white, yellow, or blue-white of other bright planets and stars. Ancient peoples noticed this and named it after gods of war and blood, reflecting its ruddy hue. The Romans called it Mars, after their god of war. The Babylonians called it Nergal, after their god of war and plague. The ancient Chinese astronomers called it the fire star. This association with warfare and blood came simply from the planet's color, visible to the naked eye across tens of millions of miles of space. When telescopes were invented and turned toward Mars, astronomers saw a world with visible surface features. They observed polar ice caps that grew and shrank with the Martian seasons. They saw areas of differing brightness and color. Some observers thought they saw networks of straight lines crisscrossing the planet. In the late 1800s, Italian astronomer Giovanni Schiaparelli described these as canali, meaning channels. This was mistranslated into English as canals, implying artificial construction. American astronomer Percival Lowell championed the idea that Mars was home to an ancient, dying civilization that had built canals to transport water from the polar ice caps to cities in the equatorial regions. This vision of Mars as a dying world inhabited by desperate, engineering-minded beings captured the public imagination. Writers like H.G. Wells and Edgar Rice Burroughs penned stories of Martian civilizations. The idea persisted until the middle of the 20th century, when better telescopes and eventually space probes revealed the truth. Mars was a cold, dry, apparently lifeless desert world. The canals were optical illusions, products of the human tendency to see patterns where none exist. The seasonal changes in surface brightness were caused not by vegetation, but by dust storms redistributing material across the planet. Yet even this more realistic picture did not diminish Mars's allure. If anything, understanding Mars as it truly is made it more fascinating. Here was an entire planet waiting to be explored, a world that might once have been warmer and wetter, a place where life might have arisen billions of years ago and might still persist in some hidden enclave. Mars orbits the Sun at an average distance of about 142 million miles, roughly 1.5 times Earth's orbital distance. This means Mars receives only about 43% as much sunlight per unit area as Earth does. Combined with Mars's thin atmosphere, this results in a cold world. The average surface temperature is around -63 degrees Celsius, though it can reach 20 degrees Celsius during summer at the equator and plunge below -140 degrees Celsius at the winter poles. The distance between Earth and Mars varies dramatically as both planets orbit the Sun. When they are on opposite sides of the Sun, they are roughly 250 million miles apart. When they are on the same side, closest approach or opposition, they can be as near as about 35 million miles, though the exact minimum distance varies from opposition to opposition due to the elliptical nature of both orbits. These close approaches occur roughly every 26 months. This variation in distance has profound implications for Mars missions. Launch windows, times when the energy required to reach Mars is minimized, occur only during certain periods related to the planet's positions. If you miss a launch window, you must wait about 26 months for the next one. The travel time to Mars depends on the trajectory chosen, but typically ranges from 6 to 9 months using current propulsion technology. Faster trajectories require more fuel, slower ones take longer but are more energy efficient. Once at Mars, simple physics dictates that you cannot immediately return. The planets must realign favorably, which takes time. A typical Mars mission profile involves traveling to Mars over 6 to 9 months, staying on the surface for about 18 to 20 months, while waiting for a favorable return window, then spending another 6 to 9 months returning to Earth. The total mission duration is thus about 30 to 33 months, nearly 3 years. This is an enormous commitment compared to any previous human space mission. The longest any person has spent in space continuously is just over 14 months, achieved by Russian cosmonaut Valery Polyakov on the Mir space station. A Mars mission would be at least twice that long and would involve far greater distance from Earth, with all the psychological implications of Earth appearing as just another star in the Martian sky. The journey to Mars presents its own challenges. The spacecraft would need to provide life support for a crew of at least 4 people, probably more like 6 to 8, to provide redundancy and allow for crew with diverse skills. They would need sleeping quarters, a common area, a kitchen or galley, storage for food and equipment, an exercise area to maintain health in microgravity, a medical bay for treating injuries or illness, a command center for piloting the spacecraft and communicating with Earth, and possibly a storm shelter, a heavily shielded area where the crew could retreat during solar particle events that increase radiation exposure. Radiation during the journey, significant concern. In interplanetary space, away from Earth's protective magnetic field, astronauts are exposed to 2 main types of radiation. Galactic cosmic rays are high-energy particles from distant supernova explosions that permeate space. These are impossible to fully shield against without impossibly thick walls. The best current approach is to accept some exposure while minimizing it through moderate shielding and fast transit times. Solar energetic particles are protons and heavier ions hurled into space during solar flares and coronal mass ejections. These are less energetic than cosmic rays, but come in intense bursts. With sufficient warning, which solar monitoring satellites can provide, crew can retreat to a specially shielded area of the spacecraft until the storm passes. The psychological challenges of the Mars journey may be as difficult as the physical ones. The crew will be confined to a small spacecraft for months. they will be unable to go outside. They will see the same faces, eat the same types of food, follow the same routines day after day. As Earth recedes to a point of light, some crew members might experience the overview effect in reverse, a profound sense of isolation and vulnerability. Communication delays will grow from seconds to minutes, eventually reaching about 22 minutes one way, when Mars and Earth are near their maximum separation. Real-time conversations become impossible. All communication becomes asynchronous, sending messages and waiting up to 44 minutes for a response. To mitigate these challenges, spacecraft designers are working on ways to make the journey more tolerable. Virtual reality could provide simulated environments, allowing crew members to feel they have escaped the confines of the spacecraft. Carefully designed crew schedules could provide variety in routine. Selection of psychologically compatible crew members who work well together is crucial. Regular communication with family on Earth, even if delayed, helps maintain connections. And meaningful work, continuous research, maintenance, and preparation for Mars landing keeps crew engaged and purposeful. Eventually, the spacecraft would arrive at Mars, entering orbit around the planet before landing. The landing itself is one of the most challenging parts of any Mars mission. Mars's atmosphere, while thin, is substantial enough to create heat during atmospheric entry. Spacecraft arriving at tens of thousands of miles per hour must slow down, but the atmosphere is too thin for parachutes alone to provide adequate braking. Past Mars missions have used a combination of heat shields, parachutes, and rocket engines in a complex sequence called entry, descent, and landing, or EDL. For crewed missions carrying much more mass than robotic probes, new EDL technologies might be needed, such as larger heat shields, supersonic retropropulsion, where rocket engines fire while moving through the atmosphere, or lifting body designs that provide aerodynamic control during descent. Once on the surface, crew would find themselves in an alien yet strangely familiar environment. Mars is the most Earth-like planet in the solar system, despite being profoundly different from Earth. The day length is nearly identical, 24 hours and 37 minutes, so close to Earth's day that human circadian rhythms would adapt easily. Mars has seasons because, like Earth, its rotation axis is tilted relative to its orbital plane. The tilt is actually slightly greater than Earth's at 25 degrees compared to Earth's 23.5 degrees. But because Mars's year is nearly twice as long as Earth's, each Martian season lasts almost twice as long. The landscape would vary depending on landing site. Mars has enormous volcanoes, the largest in the solar system. Olympus Mons rises about 13.5 miles above the surrounding plains, nearly 3 times the height of Mount Everest. It has a base roughly the size of the state of Arizona. Valles Marineris is a canyon system that dwarfs Earth's Grand Canyon, stretching about 2,500 miles long, up to 7 miles deep and 400 miles wide in some places. There are ancient impact basins, vast dune fields, polar ice caps, and plains covered with rocks and reddish dust. The sky would be salmon-colored during the day, a result of fine reddish dust particles suspended in the thin atmosphere. The sun would appear about 2/3 the size it does from Earth, noticeably smaller but still bright enough to read by. At sunset and sunrise, the situation reverses from Earth. While Earth's sunset sky is red near the horizon, fading to blue overhead, Mars's sunset sky is blue near the sun, fading to red away from it, due to the way dust particles scatter light. Dust storms are a notable feature of Martian weather. Small storms are common, but occasionally, typically during southern spring and summer, when Mars is closest to the sun, dust storms can grow to envelop the entire planet. These global dust storms can last for months, dimming sunlight and making conditions at the surface more difficult. The wind speeds during these storms, while impressive by Martian standards, are not as dangerous as they might seem. The atmospheric pressure on Mars is less than 1% of Earth's, so even a 100-mile-per-hour wind on Mars exerts only about as much force as a 10-mile-per-hour breeze on Earth. The danger is not from wind damage, but from reduced solar power and the potential for dust to interfere with equipment. Gravity on Mars is about 38% that of Earth. Someone weighing 180 pounds on Earth would weigh about 68 pounds on Mars. This is more than the Moon's 1/6 gravity, but still substantially less than Earth. Walking would feel different, with each step launching you higher and carrying you farther than on Earth. You would need to learn a new gait to avoid bouncing or stumbling. Over time, this reduced gravity might have health effects. We simply do not know whether Martian gravity is sufficient to maintain bone density and muscle mass, or whether settlers would experience gradual deterioration similar to, though perhaps less severe than, that observed in microgravity. The atmosphere is thin, but not absent. It consists of about 95% carbon dioxide, less than 3% nitrogen, less than 2% argon, and traces of other gases including oxygen, which makes up only about 0.13%. The atmospheric pressure at the surface averages about 600 pascals, compared to Earth's average of about 101,000 pascals at sea level. This pressure is below the Armstrong limit, the point at which water boils at normal human body temperature. This means unprotected humans would experience rapid evaporation of water from their lungs, eyes, and skin, leading to swift incapacitation and potentially ending in fatality within a couple of minutes. Therefore, anyone venturing outside on Mars would need to wear a pressure suit. These Martian spacesuits would be similar to those used on the Moon, but adapted for Martian conditions. They would need to maintain pressure, provide oxygen, remove carbon dioxide, regulate temperature, protect against radiation, and allow mobility. They might be somewhat lighter and more flexible than lunar suits, since Martian gravity, while low, is still more than twice lunar gravity. Dust protection would be essential, as Martian dust is pervasive and could damage seals and joints. Despite the hostile environment, Mars has resources that make settlement feasible. Water ice exists in abundance. The polar ice caps, visible from Earth through telescopes, were long known to exist. They consist of both water ice and seasonal caps of frozen carbon dioxide. Subsurface ice has been confirmed at many locations by orbiting radar and by landers that have scraped away surface dirt to reveal ice beneath. Some impact craters at high latitudes may contain nearly pure water ice deposits. The volume of water ice on Mars might rival or exceed the amount in the Great Lakes. This water could be extracted through various methods. Simple heating would cause ice to sublimate or melt, and the vapor could be condensed. Chemical extraction might use solvents or reactions to separate water from soil. Once obtained, the water would be purified and could be used for all the same purposes as on the Moon: drinking, agriculture, oxygen production, and creating rocket fuel. The Martian atmosphere, while too thin to breathe, is a valuable resource. Carbon dioxide can be processed to extract oxygen through chemical reactions or by using plants in greenhouses. The Sabatier reaction, a well-understood chemical process, combines carbon dioxide with hydrogen to produce methane and water. This reaction has been demonstrated on Mars by the MOXIE experiment on NASA's Perseverance rover, which successfully produced oxygen from the Martian atmosphere. For a settlement, scaled-up versions of such technology could provide all the oxygen needed for breathing and then some. Methane produced from the Sabatier reaction could be used as rocket fuel when combined with oxygen. This is the propellant combination that several Mars mission concepts plan to use. A spacecraft that arrives at Mars with hydrogen, but produces methane and oxygen locally, would not need to carry fuel for the return journey, dramatically reducing the mass that must be launched from Earth. The soil, or regolith, contains useful elements. Iron oxides give Mars its red color and could be reduced to extract iron metal. Silicon is abundant and could be made into glass, semiconductors, or photovoltaic cells. Aluminum, titanium, magnesium, and other metals are present and could be extracted through various industrial processes. Sulfur exists in the soil and could be used as a binding agent for Martian concrete, a building material made from regolith without needing water. Martian habitats would need to be robust structures, capable of withstanding pressure differentials and protecting inhabitants from radiation. Initial habitats might be prefabricated modules sent from Earth, similar to those used on the International Space Station, but adapted for Martian conditions. These would be landed and then covered with several meters of Martian soil for radiation protection. As the settlement develops, construction using local materials would become increasingly important. Bricks could be made from Martian regolith, compacted under high pressure, creating strong building materials without need for firing in kilns. Sulfur-based concrete could be mixed on Mars and used to construct walls and structures. Three-dimensional printers designed to work with Martian materials could fabricate complex components. Underground habitats could be excavated in suitable locations, taking advantage of natural protection from radiation and temperature extremes. One particularly intriguing possibility is utilizing Martian lava tubes, just as on the Moon. Mars has extensive volcanic features, and where lava once flowed, tubes likely formed. Some of these tubes might be enormous, capable of housing entire communities. Exploring and characterizing these formations would be an important early priority, as they could provide ready-made spaces for habitation, requiring less construction effort than building from scratch. Greenhouses would be essential for a Mars settlement. While initial missions would bring all food from Earth, this is not sustainable for a permanent settlement. Greenhouses could be inflatable structures made from transparent or translucent materials, positioned on the surface or integrated into habitat modules. Inside, plants would grow in hydroponic or aeroponic systems. The carbon dioxide-rich Martian atmosphere would be introduced into the greenhouse, providing plants with abundant raw material for photosynthesis. Lighting might be provided by sunlight, filtered through the greenhouse walls, supplemented by artificial lighting when needed. The plants would produce oxygen, creating a synergistic cycle where humans breathe oxygen and exhale carbon dioxide, which plants then convert back into oxygen. Growing food on Mars would require careful selection of crops. Fast-growing, nutrient-dense plants like potatoes, wheat, soybeans, and various vegetables would likely be priorities. Leafy greens like lettuce, spinach, and kale grow quickly and provide vitamins. Research on the International Space Station and in ground-based analogues has already demonstrated that many common Earth plants can grow successfully in space-like conditions. The challenge on Mars would be providing adequate light, maintaining proper temperature and humidity, and protecting plants from the Martian environment while allowing enough sunlight to reach them. Power generation on Mars presents different challenges than on the Moon. Solar power is feasible, but Mars receives less sunlight than Earth, and dust storms can block sunlight for extended periods. Solar panels would need to be larger for the same power output compared to Earth or the Moon. They would also need to be kept clean of dust, either through robotic wiping systems or by tilting them to allow dust to slide off. Despite these challenges, solar power will likely be the primary energy source for early Mars settlements. Nuclear power provides an alternative or supplement. Small modular reactors designed for space applications could provide continuous baseline power regardless of solar conditions. They would be especially valuable during global dust storms, when solar power might be severely curtailed. Nuclear reactors for Mars would need to be highly reliable, compact, and capable of operating with minimal maintenance for years. Transportation on Mars would initially be limited to the landing site vicinity. Pressurized rovers, similar to those planned for the Moon but adapted for Martian conditions, would allow exploration of the surrounding region. These rovers would need to handle varied terrain, from soft sand to rocky outcrops. They would need to be largely autonomous or remotely operable from the habitat, as suited exploration is more challenging on Mars than on the Moon due to the planetary dust and the need for more complex life support systems. Long-distance travel on Mars might eventually utilize aircraft. The thin atmosphere makes flight difficult, but not impossible. Mars helicopters would operate more like Martian drones, with large rotors spinning very fast to generate lift in the thin air. NASA's Ingenuity helicopter, which accompanied the Perseverance rover, successfully demonstrated powered flight on Mars in 2021, paving the way for more capable future aircraft. Fixed-wing aircraft are also possible, and might be more efficient for covering large distances. Such aircraft could enable rapid travel between settlements or allow exploration of areas far from the main base. Communication infrastructure on Mars would be more complex than on the Moon, due to the greater distance from Earth. Direct communication requires waiting minutes for signals to travel each way. To support extensive surface operations, Mars would need a network of communication satellites in orbit, providing coverage for rovers, aircraft, and human explorers wherever they might be on the planet. These satellites would relay signals back to Earth via the Deep Space Network, the collection of large radio antennas that NASA operates in California, Spain, and Australia to communicate with distant spacecraft. Science on Mars would be extraordinarily rich. The geology of Mars preserves a record of the early solar system. Ancient rocks contain clues about Mars's past climate and whether it once had liquid water on its surface. Finding evidence of past life, or perhaps even extant life in subsurface aquifers or other protected environments, would be one of the most profound discoveries in human history. Even if life never arose on Mars, understanding why not, when it did arise on Earth, despite the planet's similarities in their youth, would teach us about the nature and frequency of life in the universe. Martian settlers would become planetary scientists by necessity, studying their new home to better understand and utilize it. They would search for the best sources of water ice, the most useful mineral deposits, the safest locations for expansion. They would monitor weather patterns to predict dust storms. They would study the subsurface structure to understand where tunnels could safely be dug. And they would look for signs of past or present life, perhaps making the most important scientific discovery ever made. The timeline for Mars settlement necessarily extends further into the future than that for the Moon. The first crewed Mars mission might launch in the late 2030s or early 2040s if current plans proceed without major delays. This first mission would be a flags and footprints endeavor, establishing that humans can travel to Mars, live there for an extended period, and return safely. Subsequent missions would occur every 26 months during favorable launch windows, each staying longer and accomplishing more than the previous one. By the 2050s or 2060s, a small but permanent research base might exist, hosting a dozen or so people who rotate through on 30-month tours. This base would be analogous to research stations in Antarctica, continuously occupied, but with a transient population. It would serve as a platform for scientific research, a test bed for technologies needed for larger settlements, and a symbol of human presence on another planet. A truly self-sustaining settlement on Mars, capable of surviving indefinitely without resupply from Earth, would represent a much greater challenge. Such a settlement would need to produce its own food, manufacture its own equipment and spare parts, generate its own power, and maintain its life support systems using only Martian resources. It would need a large enough population to include people with diverse skills: farmers, engineers, doctors, technicians, teachers, administrators. It would need industrial capacity to refine materials, fabricate components, and repair or replace everything from spacesuits to habitat modules. Achieving this level of self-sufficiency might not occur until late in this century, or even into the 22nd century. A Mars settlement would need to be largely self-sufficient due to the enormous distance from Earth. The journey time and the expense of each mission mean that resupply missions would be infrequent and costly. Settlers would need to produce as much as possible locally, using resources available on Mars. This approach is called in situ resource utilization, often abbreviated ISRU, and it represents one of the key technologies that will make Mars settlement feasible. Water is the foundation of everything. Fortunately, Mars has substantial water ice deposits. The polar regions contain vast ice caps, but these are far from ideal landing sites due to extreme cold and seasonal darkness during winter. More accessible water ice exists in mid-latitude regions, buried beneath a layer of dust and soil. This ice is believed to be the remnant of snow that fell during past climatic periods when Mars's axial tilt was greater than it is today. Orbiting radar has mapped these deposits, revealing layers of relatively pure ice extending meters below the surface in some regions. Mining this ice would involve digging trenches or drilling holes to reach the ice layer, then heating it to cause sublimation or melting. The resulting water vapor could be collected and condensed. This water would then be purified to remove any contaminants, though Martian ice is expected to be relatively clean compared to ice on Earth, which contains organic compounds and dissolved minerals. Once purified, the water could be used for all the purposes essential to human life and industrial activity. Through a process called electrolysis, water can be split into its constituent elements, hydrogen and oxygen. This requires electricity, which would be supplied by solar panels or nuclear reactors. The oxygen produced could be compressed and stored for use as breathable air. The hydrogen could be stored separately and used in various chemical processes or as fuel. Importantly, hydrogen combined with carbon dioxide from the Martian atmosphere can produce methane through the Sabatier reaction, providing locally made rocket fuel. This reaction also produces water as a byproduct, which can be recycled back into the system. The Sabatier reaction has been understood for over a century, but only recently demonstrated on Mars itself. The MOXIE experiment aboard NASA's Perseverance rover, which landed in 2021, successfully converted Martian carbon dioxide into oxygen. MOXIE is a small device, about the size of a toaster, but it proved the concept works on Mars's surface. A full-scale system for a settlement would be much larger, capable of producing tons of oxygen and methane per year. The Martian atmosphere, though thin, is a resource as well as a challenge. It consists primarily of carbon dioxide, which plants can use directly for photosynthesis in greenhouses. The atmosphere also contains trace amounts of nitrogen, essential for plant growth and for creating breathable air with the proper gas mixture. While Mars's nitrogen is scarce compared to Earth's, enough could be extracted over time to meet settlement needs. Various chemical and physical processes could concentrate nitrogen from the atmosphere. Beyond water and atmospheric gases, the Martian soil contains useful minerals and elements. Iron is abundant, giving the planet its characteristic red color from iron oxide rust. This iron could be extracted through chemical reduction processes, heating the iron oxide with carbon or hydrogen to drive off the oxygen and leave metallic iron. The iron could then be melted, alloyed with other elements to create steel, and fabricated into structural beams, plates, tools, and machinery. Silicon is another abundant element on Mars. Silicon dioxide, also known as silica or quartz, exists in Martian rocks. Silica can be melted and formed into glass for windows, lenses, and protective barriers. It can also be refined into highly pure silicon for making solar cells, semiconductor electronics, and computer chips. While the processes for doing this are complex and energy-intensive, they are well understood from terrestrial industries. Aluminium, though requiring significant energy to extract from its ores, is valuable for space applications due to its low density and high strength-to-weight ratio. Mars has aluminum-rich minerals that could be processed to obtain this useful metal. Titanium, even stronger and lighter than aluminum for its strength, also exists in Martian rocks and could be extracted, though this would require advanced metallurgical capabilities. Sulfur in the Martian soil has already been mentioned as a potential binding agent for concrete. Martian sulfur concrete would be mixed at moderate temperatures, around 140 degrees Celsius, much lower than the over 1,000 degrees needed for traditional cement kilns. The sulfur acts as a thermoset polymer, solidifying as it cools and binding the regolith particles together. The resulting material is strong, durable, and completely made from local resources, except for the energy needed to heat it. Building materials created from Martian resources could enable extensive construction without importing massive amounts of material from Earth. Habitats, greenhouses, workshops, storage facilities, landing pads, roads, and eventually even manufacturing plants could all be built using varying combinations of regolith concrete, metal plates and beams, and glass panels. Three-dimensional printing technology, adapted for Martian materials, could construct complex shapes layer by layer, potentially even printing entire habitat structures. Food production on Mars would transform the settlement from a research outpost into a true home. Initial missions would bring all food from Earth, relying on freeze-dried meals, canned goods, and other preserved foods, similar to what astronauts eat on the International Space Station. But this is not sustainable for a permanent settlement. A closed-loop agricultural system would need to be developed, where plants grow using Martian resources, producing food for the crew while also recycling air and water. Martian greenhouses would be complex environments, carefully designed to support plant growth. They would need to maintain pressure, temperature, humidity, and light levels within ranges suitable for plants. The Martian atmosphere could be introduced, but would need to be supplemented with oxygen and nitrogen to create a breathable environment for people who need to enter the greenhouse to tend plants. Alternatively, greenhouses might be filled with pure carbon dioxide at higher pressure, optimizing for plant growth, but requiring workers to wear respirators when inside. Lighting in greenhouses could come partially from sunlight passing through transparent walls, but the lower light intensity on Mars compared to Earth might require supplementation with artificial lighting. Light-emitting diodes have become efficient enough that providing artificial lighting for plants is energetically feasible. Different wavelengths of light could be provided based on what the plants need most, rather than trying to replicate the full solar spectrum. The growing medium could be Martian regolith that has been processed to remove harmful perchlorates, naturally occurring chemicals that are toxic to humans and plants. Once cleaned, the regolith could be enriched with organic matter from composted plant waste and human waste products, gradually transforming it into something more like earth soil. Alternatively, hydroponic systems where plant roots are suspended in nutrient solutions, or aeroponic systems where roots hang in air and are misted with nutrients, could avoid the complications of using Martian soil directly. Crop selection for Mars would prioritize caloric output, nutritional balance, and psychological value. Potatoes are often mentioned as an ideal Mars crop because they produce high yields of calories in compact space and can be prepared in numerous ways. Wheat could be grown for making bread, pasta, and other grain-based foods. Soybeans provide protein and can be processed into tofu, soy milk, and other products. Rice might also be grown, though its water requirements could be a concern. Various vegetables would provide vitamins, minerals, and fiber. Lettuce, tomatoes, peppers, carrots, beans, peas, and more. Beyond utilitarian food crops, the psychological benefits of having fresh, flavorful food cannot be overstated. Herbs and spices would be valuable for adding variety to meals. Strawberries, though not calorically dense, would provide a special treat and boost morale. Even flowers might be grown in small quantities, adding color and beauty to the environment. Studies of people in isolated environments consistently show that access to fresh food and living plants significantly improves mood and mental health. Animal protein would be more challenging to produce on Mars. Bringing livestock would require significant resources, both for the animals themselves and for producing their feed. Fish might be more practical, raised in aquaculture systems that integrate with the overall life support ecology. Insects like crickets or mealworms are efficient protein sources, requiring minimal space and resources. While Western cultures are not traditionally insect-eating, other cultures have long histories of entomophagy, and insects might become a standard protein source for Mars settlers. Cellular agriculture, growing meat from cell cultures without raising entire animals, might eventually provide another option, though this technology is still developing on Earth. The question of reproduction on Mars raises profound medical and ethical questions. If a settlement is to be truly permanent, children will eventually be born there. But pregnancy and child development in Martian gravity are completely unstudied. Would the reduced gravity affect fetal development? Would children born and raised in Martian gravity develop properly? Would they be able to adapt to Earth gravity if they later visited? Or would they be permanently adapted to Mars? We can speculate based on what we know, but speculation is all we have. Earth's gravity shaped mammalian development over hundreds of millions of years. Every aspect of how bodies form, from the way cells divide and differentiate to how bones grow and muscles develop, occurs under 1 g of acceleration. Martian gravity is only 0.38 g. This might be close enough that development proceeds normally, or it might not. The only way to know for certain would be through experience, and the ethical implications of potentially condemning children to lives unable to return to Earth are staggering. Some scientists and ethicists argue that reproduction on Mars should be postponed until we have much better understanding of the effects of partial gravity on development. Others argue that permanent settlement inherently requires accepting some level of irreversibility, and that children born on Mars would be Martians, adapted to their home world, not imperfect versions of Earth humans. These debates will intensify as Mars settlement becomes more realistic. The governance of a Mars settlement presents interesting challenges. Early settlements would likely operate under the authority of whatever space agency or company established them, with clearly defined command structures and rules. But as settlements grow and include more diverse populations staying for longer periods, questions of self-governance would arise. Would Mars settlers have a voice in decisions affecting their lives? Would they be citizens of Earth nations or of Mars itself? Could Mars eventually become independent, a sovereign entity separate from Earth? International space law currently prohibits nations from claiming sovereignty over celestial bodies. The Outer Space Treaty, signed by over 100 nations, including all major spacefaring powers, declares that outer space, including the Moon and other celestial bodies, is the province of all mankind and not subject to national appropriation. This means no nation can claim Mars as its territory. However, the treaty is less clear about the rights of individuals or companies, and whether settlements could claim independence, or at least self-governance rights. As settlements grow, they would need systems for resolving disputes, allocating resources, making collective decisions, and maintaining order. Would Earth laws apply on Mars? And if so, which nations' laws? Would a new legal framework need to be developed specifically for space settlements? These questions echo debates from Earth's history about colonies and their relationships with founding nations, though the profound distance and communication delays between Earth and Mars would create circumstances unlike any terrestrial colonization. Cultural development on Mars might follow interesting paths. Settlers coming from various Earth nations and cultures would bring their diverse backgrounds and traditions. Over time, a unique Martian culture would likely emerge, shaped by the specific challenges and opportunities of life on Mars. Language might evolve new vocabulary and possibly new accents or dialects, as has happened in isolated human populations throughout history. Art and music created on Mars would reflect the Martian experience. Literature and poetry might explore themes of exile, adaptation, and transformation. In time, people might identify more as Martians than as members of whatever Earth culture they or their ancestors came from. Beyond the Moon and Mars, what other possibilities exist for human habitation in space? One intriguing option is orbital space habitats. Rather than living on the surface of another world, humans could construct enormous, rotating cylindrical or toroidal structures in orbit around Earth, the Moon, or other bodies. These habitats would spin to create artificial gravity through centrifugal force. This approach solves the gravity problem, providing Earth normal weight without needing to live on a massive planet. The concept of space habitats was developed in detail during the 1970s by physicist Gerard O'Neill and his students at Princeton University. The designs ranged from relatively small cylinders housing thousands of people to enormous structures called O'Neill cylinders, potentially housing millions. These massive constructions would be several miles long and miles in diameter, containing entire communities with parks, towns, agriculture, and industry. Building such structures would require enormous amounts of material. Launching all that mass from Earth would be prohibitively expensive. Instead, space habitat proponents suggest mining asteroids and the Moon for raw materials. The materials would be processed in space and used to construct the habitats. With sufficient automation and robotic labor, the process could become increasingly efficient over time. Space habitats would have several advantages. Residents could control the environment precisely, including gravity level, atmosphere composition, temperature, and light cycles. They could be positioned in locations that receive continuous solar power. They could be expanded indefinitely by building additional modules, and they would not be vulnerable to planetary-scale disasters. However, space habitats also face significant challenges. The initial construction would require massive investment and technological development. Maintaining the structural integrity of such large rotating structures would be complex. Any breach in the hull could be catastrophic. And questions about governance, society, and long-term sustainability would need to be addressed. Despite these challenges, there is renewed interest in space habitats. Several private companies are developing inflatable habitat technology that could serve as stepping stones toward larger structures. The International Space Station has demonstrated that humans can live in space for extended periods, up to a year or more. The Lunar Gateway, a planned space station in orbit around the Moon, will provide additional experience with deep space habitation. Another possibility for human habitation is within asteroids themselves. Near-Earth asteroids are numerous, and many are large enough to contain substantial cavities. Some researchers have proposed hollowing out asteroids and creating habitats within them. The asteroid material would provide natural radiation shielding. The rock could be mined for useful materials, and the entire structure could potentially be moved to more convenient locations using slow, steady propulsion over long periods. This concept might sound far-fetched, but it has been studied seriously. The technical challenges are substantial, but not insurmountable. Robotic mining equipment could excavate the interior. The extracted material could be used for construction or exported for use elsewhere. Life support systems could be installed inside the hollowed space. The main difficulty would be reaching the asteroids in the first place and establishing the initial infrastructure to begin mining and construction. Venus, our other nearby planet, presents a very different possibility. The surface of Venus is utterly inhospitable. With temperatures exceeding 460 degrees Celsius and atmospheric pressure 90 times that of Earth, no human could survive there without extraordinary technology. However, high in Venus's atmosphere, conditions are remarkably Earth-like. At an altitude of about 50 kilometers above the surface, the temperature is around 25 degrees Celsius, and the pressure is similar to Earth's at sea level. A habitat floating in Venus's clouds could potentially provide a comfortable living environment. The atmosphere at that altitude is dense enough to provide buoyancy. A habitat filled with breathable air would actually float in the Venusian atmosphere, because oxygen and nitrogen are lighter than carbon dioxide. Solar power would be abundant. The only downsides are the sulfuric acid in the clouds, which would require acid-resistant materials, and the fact that you could never easily reach the surface or leave. Still, as a long-term possibility for human settlement, cloud cities on Venus are an intriguing option. The outer solar system presents even more exotic possibilities. The moons of Jupiter and Saturn have their own unique characteristics. Europa, a moon of Jupiter, has a subsurface ocean beneath its icy crust that might contain more water than all of Earth's oceans combined. Titan, Saturn's largest moon, has a thick atmosphere and lakes of liquid methane on its surface. These worlds are so distant and cold that settlement there is beyond current technological capability. But they represent potential locations for future human expansion if we can solve the problems of distance, radiation in Jupiter's intense magnetic field, and extreme cold. Having explored the locations, let us now turn to the challenges that any off-Earth settlement must overcome. The first and most fundamental challenge is life support. On Earth, we take for granted the constant availability of air, water, and comfortable temperatures. In space or on other worlds, all these must be artificially maintained. Air is relatively straightforward in principle. Humans need oxygen to breathe and exhale carbon dioxide. Plants and certain chemical processes can convert carbon dioxide back into oxygen. A well-designed life support system recycles the air continuously. The International Space Station currently recycles about 93% of its water and a high percentage of its oxygen. Future systems aim for even higher efficiency, approaching 98 or 99% recycling. However, perfect recycling is impossible. Some oxygen is always lost through leakage or chemical reactions. This means any off-Earth settlement needs either a steady supply of oxygen from Earth or a way to extract it locally. On the Moon and Mars, oxygen can be extracted from water ice or from oxide minerals in the soil. In space habitats, supplies would need to come from asteroids or other sources. Water recycling faces similar issues. Every drop of water is precious in space. Wastewater from washing, humidity in the air, and even urine must be purified and reused. Current systems can recycle water very efficiently, but not perfectly. Losses must be replaced. Fortunately, water appears to be relatively common in the solar system. Ice exists on the Moon, Mars, asteroids, and many outer solar system moons. The challenge is extracting and purifying it. Temperature control is another critical aspect of life support. In space, the vacuum provides excellent insulation, which can be both helpful and problematic. Without an atmosphere to carry heat away, cooling spacecraft and habitats requires radiators that emit thermal radiation into space. On the Moon and Mars, temperature extremes require habitats with excellent insulation and active heating or cooling systems. The design must balance the need to retain heat in cold environments with the need to dissipate heat generated by people and equipment. Radiation protection is one of the most serious challenges for human life beyond Earth. On our planet, we are protected by the atmosphere and Earth's magnetic field. These shield us from harmful solar and cosmic radiation. In space, on the Moon or on Mars, that protection is absent or greatly reduced. There are several types of space radiation to consider. Solar radiation comes from the Sun, particularly during solar flares and coronal mass ejections. This consists mainly of energetic protons. Galactic cosmic rays come from distant exploding stars and consist of high-energy atomic nuclei, including heavy ions. Both types can damage human cells, increasing cancer risk and potentially causing acute radiation sickness during severe events. Radiation shielding requires mass. Thick walls of metal, rock, ice, or other materials can absorb or deflect radiation particles. On the Moon and Mars, this means building habitats underground or covering them with several meters of regolith. In space habitats, water walls or polyethylene shields might be used. However, perfect protection is difficult. Thick shielding is heavy and expensive. Some mission designs accept higher radiation exposure and focus on minimizing risks through shorter missions, radiation-resistant habitat design, and medical monitoring. Artificial magnetic fields have been proposed as a way to deflect charged particles. While this technology exists in principle, creating a field strong enough to protect a large area requires enormous amounts of power. It remains a possibility for future settlements, but is not practical with current technology. The effects of reduced gravity on human health are still being studied. We know from decades of experience on the International Space Station that microgravity causes significant health problems. Bones lose density at a rate of about 1 to 1.5% per month. Muscles atrophy, particularly in the legs and back. The cardiovascular system weakens, fluids shift toward the head, causing facial puffiness and increased pressure in the eyes, which can lead to vision problems. The immune system weakens. Even the shape of the eyeball can change, causing permanent vision alterations in some astronauts. Exercise can mitigate some of these effects. Astronauts on the space station exercise for 2 hours daily using specialized equipment. However, this does not completely prevent bone and muscle loss. After returning to Earth, recovery takes months, and some effects may be permanent. The Moon's 1/6 gravity and Mars's 3/8 gravity may be better than microgravity, but we simply do not know. No human has spent more than a few days in lunar gravity, and no human has yet been to Mars. It is possible that these partial gravity environments are sufficient to maintain health. Or, it is possible that humans would still experience gradual deterioration. Research into artificial gravity through rotating spacecraft or habitats may provide solutions. Psychological and social factors are equally important as physical challenges. Humans are social creatures who evolved in rich, varied environments. Confining people in small spaces with limited social interaction for extended periods can lead to psychological stress, conflict, and mental health issues. Isolation is one aspect. Being millions of miles from Earth, knowing that no rescue is possible in an emergency, and facing communication delays can be profoundly stressful. Monotony is another factor. The same environment, the same people, the same routines, day after day, can wear on mental health. Lack of privacy in confined spaces creates tension. Even minor interpersonal conflicts can escalate without the ability to escape or de-escalate. Space agencies study these factors carefully. Crew selection emphasizes psychological stability, social skills, and the ability to handle stress. Analog missions in extreme environments on Earth, such as simulated Mars habitats in remote locations, help researchers understand the psychological challenges and develop countermeasures. These include structured schedules, private sleeping quarters, recreational activities, regular communication with loved ones on Earth, and access to entertainment and educational materials. Some researchers suggest incorporating nature into habitats. Greenhouses where crops grow serve not only practical purposes, but also psychological ones. Seeing green plants, caring for living things, and experiencing the cycles of growth and harvest can provide comfort and purpose. Even small touches, like wood paneling, nature sounds, and images of Earth landscapes might help maintain mental well-being. The question of governance and society in space settlements raises fascinating issues. Who makes the rules on a Mars base? How are disputes resolved? What economic systems would develop? These questions have no clear answers yet. Early settlements will likely operate under the authority of the space agencies or companies that establish them. Residents might be employees or researchers with limited autonomy. However, as settlements grow and become more permanent, residents may desire more self-governance. The history of terrestrial colonization provides both cautionary tales and potential models, though the unique constraints of space settlement make direct analogies imperfect. International law currently governs space activities. The Outer Space Treaty of 1967 establishes that celestial bodies cannot be claimed by nations. Space is considered the province of all mankind. Commercial exploitation is not clearly regulated. As space activities increase, these legal frameworks will need to evolve. Questions about property rights, resource extraction, and sovereignty will need answers. Economic viability is another major question. How would space settlements support themselves financially? Early settlements will depend entirely on support from Earth, requiring constant resupply missions costing billions of dollars. For settlements to become sustainable, they need to provide value that justifies this investment. One possibility is scientific research. The Moon provides an excellent platform for astronomy, particularly radio astronomy far from Earth's interference. Mars offers unparalleled opportunities to study planetary science, geology, and possibly the origins of life. The knowledge gained might justify the expense. Another possibility is resource extraction. Mining the Moon or asteroids for valuable materials that can be used in space or returned to Earth could become profitable. Platinum group metals, rare earth elements, and water ice all have value. However, the economics are uncertain. Extracting these resources requires substantial upfront investment in mining equipment and transportation infrastructure. Whether the value of materials justifies this investment remains to be seen. Space-based manufacturing offers intriguing possibilities. Certain materials and processes might benefit from microgravity environments. Crystals for semiconductors, fiber optics, and pharmaceuticals might be produced more efficiently in space. Manufacturing large structures like space habitats or solar power satellites might be easier when not fighting Earth's gravity. As the space economy develops, entirely new industries might emerge. Tourism is another potential revenue source. While currently limited to the extremely wealthy, space tourism could eventually become more accessible. A hotel on the Moon or in orbit might attract visitors willing to pay substantial sums for the experience. However, tourism alone is unlikely to support large settlements. It would be one component of a diversified space economy. The technologies required for space settlement are advancing rapidly, though significant hurdles remain. Launch costs have decreased dramatically in recent years due to reusable rockets developed by companies like SpaceX and Blue Origin. This trend is likely to continue. However, even with lower launch costs, the expense of transporting people and equipment to the Moon or Mars remains substantial. Robotics and automation will play crucial roles. Before humans arrive, robotic systems could prepare landing sites, begin mining operations, construct initial infrastructure, and test systems. This approach reduces risk and expense. Advances in artificial intelligence and remote operation make this increasingly feasible. Three-dimensional printing technology adapted for space applications could revolutionize construction. Rather than launching finished structures from Earth, settlements could manufacture components on site using local materials. Researchers have already demonstrated 3D printing using simulated lunar and Martian regolith. Future printers might construct habitat modules, tools, spare parts, and other necessities. Biotechnology will be essential for food production and life support. Traditional agriculture is possible in space, but requires significant resources. Hydroponic and aeroponic systems that grow plants without soil are more efficient. Algae and other microorganisms could recycle waste and produce food and oxygen. Some researchers even propose using genetically engineered organisms specifically designed for space environments. Energy systems must be reliable and efficient. Solar power works well on the Moon and Mars, though Mars's dusty atmosphere reduces efficiency. Energy storage systems like batteries or fuel cells are needed for periods when the sun is not available. Nuclear power, particularly small modular reactors, could provide continuous baseline power. In the longer term, fusion power might revolutionize space energy systems, though practical fusion remains elusive. Communication infrastructure is already being developed. Current Mars missions rely on a network of orbiting satellites and Earth-based deep space communication facilities. As activity increases, more sophisticated networks with higher bandwidth will be needed. Communication delays cannot be eliminated, but data transmission rates can be improved. Let us also consider the ethical dimensions of space settlement. Is it right to expand human presence beyond Earth? Does humanity have the right to exploit the resources of other worlds? What responsibilities do we have to preserve the pristine nature of these environments? Some argue that space exploration and settlement are essential for humanity's long-term survival and flourishing. They see it as a natural extension of human curiosity and capability. Others worry about repeating the mistakes of terrestrial colonization, where exploration often led to exploitation and harm. They advocate for careful consideration and strong ethical guidelines before proceeding. The question of planetary protection is particularly important for Mars and other worlds where life might exist. If Mars harbors microbial life in underground aquifers, elsewhere, human contamination could harm or eliminate these organisms before we even discover them. Protocols currently require sterilization of spacecraft sent to Mars to minimize this risk. As human missions proceed, maintaining this protection becomes more difficult but remains important. There is also the question of transforming other worlds. Terraforming, the theoretical process of altering a planet's environment to make it more Earth-like, has been proposed for Mars. This might involve thickening the atmosphere, warming the surface, and potentially establishing an environment where humans could breathe outside without spacesuits. However, such massive environmental engineering raises profound ethical questions. Do we have the right to fundamentally alter another world? What if life exists there in forms we do not recognize? Let us also think about who gets to go to space and who benefits. Currently, space access is limited to highly trained astronauts and increasingly wealthy tourists. For space settlement to be more than an exclusive enclave of elites, it must eventually become accessible to a broader range of humanity. This raises questions of equity, opportunity, and purpose. Will space settlements be diverse, inclusive communities representing all of humanity? Or will they reflect and potentially amplify existing inequalities? Education and preparation of the next generation will be crucial. Space settlement will require people with diverse skills: engineers, scientists, medical professionals, farmers, educators, artists, and many others. Inspiring young people to pursue these fields and preparing them for the unique challenges of space life is already beginning. Universities offer programs in aerospace engineering and planetary science. Space camps and educational programs introduce children to space concepts. As settlements become more concrete, education systems will need to adapt further. The timeline for large-scale human settlement beyond Earth is measured in decades and centuries, not years. Near-term goals for the 2020s and 2030s include establishing initial lunar bases and perhaps the first crewed Mars missions. The 2040s and 2050s might see small but permanent settlements on the Moon and possibly Mars, each hosting dozens to hundreds of people. By the end of this century, if development proceeds well, we might see settlements housing thousands of people, with the beginnings of true self-sufficiency. Beyond that, the possibilities expand dramatically. The 22nd and 23rd centuries might see millions of people living off Earth, in settlements throughout the inner solar system. Space habitats could host large populations in Earth orbit or at strategically important locations. Mars might have growing cities, slowly being made more habitable through centuries of environmental engineering. The asteroid belt could be dotted with mining colonies. Even the outer solar system might host human outposts. This vision requires optimism about human capability and cooperation. It assumes that we continue to develop technology, that we find ways to make space settlement economically viable, that we avoid catastrophic conflicts or collapses that divert resources away from space. These are not guaranteed. History shows that grand projects can falter, that priorities shift, that what seems inevitable can be delayed or abandoned. Yet there are reasons for optimism. Humanity has repeatedly demonstrated remarkable capability when motivated. We went from the first powered flight to landing on the moon in just 66 years. We built the International Space Station, a marvel of engineering and international cooperation. We have sent robots to every planet in the solar system and even landed them on asteroids and comets billions of miles away. These achievements show what is possible when we commit to grand goals. The technologies developed for space settlement often have applications on Earth. Better life support systems could help submarine crews or people in extreme environments. Advanced materials developed for spacecraft could improve construction or transportation. Water recycling systems designed for Mars could help address water scarcity on Earth. The benefits of space technology often flow back to improve life on our home planet. Moreover, the perspective gained from seeing Earth from space has had profound impacts. Astronauts speak of the overview effect, a shift in consciousness from seeing our planet as a small, fragile sphere in the vast darkness. This perspective emphasizes the unity of humanity and the importance of protecting our planetary home. As more people experience space, this perspective might become more widespread, potentially influencing how we treat Earth and each other. The question of whether humans can live beyond Earth is no longer purely theoretical. We have the basic technology. We understand the challenges. What remains is the commitment, the resources, and the time to make it happen. And it will happen, not because it is easy, but because it is part of who we are as a species. We are explorers. We are builders. We look at empty places and imagine them filled with life and purpose. The Moon, Mars, and the rest of the solar system are not empty in the sense that they lack value or meaning. They are empty in the sense that they await the touch of life, the presence of consciousness, the transformation that only living things can bring. In establishing ourselves beyond Earth, we continue a process that began billions of years ago, when the first simple cells appeared in Earth's oceans. Life has always expanded, exploring new environments, adapting to new challenges, spreading wherever conditions permit. We are simply the latest manifestation of that ancient drive, now reaching out to the cosmos itself. There is something profound in this. We are made of star stuff, as the astronomer Carl Sagan famously said. The atoms in our bodies were forged in the hearts of ancient stars. The iron in our blood, the calcium in our bones, the carbon in our DNA, all were created in stellar furnaces and scattered across space when those stars ended their lives. We are the universe becoming conscious of itself, and in reaching for the stars, we are in a sense returning home. As you lie here, listening to these words, think about what it means. You are a collection of atoms arranged in an impossibly intricate pattern, conscious and curious. You exist on a small planet, orbiting an ordinary star in a galaxy containing hundreds of billions of stars, in a universe containing hundreds of billions of galaxies. The fact that you exist at all is extraordinary. The fact that your species might soon spread to other worlds is even more remarkable. But do not let the grandeur of these ideas overwhelm you. They are meant to inspire wonder, not anxiety. The universe is vast and we are small, but that is beautiful, not frightening. We are small in scale, but infinite in potential. So, what would life actually be like for someone living on the Moon or Mars? Let us imagine it, gently, as you settle deeper into rest. You wake in your sleeping compartment, a small but comfortable space about the size of a walk-in closet. The ceiling glows softly simulating a sunrise. This is important because your circadian rhythms need light cues to function properly. The light gradually brightens over 20 minutes, gently rousing you from sleep. You float out of bed. If you are in a space habitat with artificial gravity from rotation, you walk normally. If you are on the moon or in low gravity, your movements are slower, more deliberate. You have learned to control your strength because pushing too hard sends you sailing upward. The bathroom is efficient. Water for washing is rationed but adequate. You use a specialized shower that captures and recycles every drop. The toilet is more complex than on Earth, using airflow instead of water, but you have grown accustomed to it. Your toothbrush and other personal items are secured with magnets or Velcro to prevent them from floating away in low gravity. Breakfast is in the common area, a larger space where the habitat's crew gathers. Some food comes from greenhouses, fresh vegetables and herbs that taste wonderful after months of preserved and packaged meals. Other food is freeze-dried or vacuum-sealed, brought from Earth. Coffee is a precious commodity. Water for drinking has been recycled many times, purified so thoroughly it is cleaner than most water on Earth, though the idea still takes mental adjustment. After breakfast, you head to your workstation. If you are a scientist, you might be analyzing geological samples, monitoring weather patterns, or conducting biological experiments. If you are an engineer, you might be maintaining life support systems, repairing equipment, or overseeing construction robots. If you are a farmer, you spend your day in the greenhouse, tending plants that provide food and oxygen while removing carbon dioxide from the air. The work is purposeful and often challenging. Equipment fails in unexpected ways. Problems that would be minor on Earth become significant when you cannot simply order a replacement part. Improvisation and creativity are essential skills, yet there is deep satisfaction in overcoming these challenges, in making a hostile environment habitable through ingenuity and persistence. Midday, you might take a break to exercise. This is not optional. You must exercise at least 2 hours daily to maintain bone density and muscle mass. The exercise equipment is specialized, designed for the gravity environment you are in. You run on a treadmill while wearing a harness that pulls you down, simulating weight. You lift resistance devices that challenge your muscles. You do exercises that stress your bones in specific ways to prevent deterioration. Lunch is another social time. The crew has become close, almost like family. You share stories, jokes, frustrations. Sometimes there is tension, conflicts that arise from close quarters and high stress. But there is also camaraderie, a bond formed by shared experience and mutual dependence. You rely on each other completely. The afternoon brings more work. Perhaps today you go outside for a surface excursion. You spend 30 minutes putting on your spacesuit, checking every seal and system. Your buddy does the same. You go through checklists together, confirming that everything functions correctly. Then you enter the airlock, wait as the air is pumped out, and step outside. The landscape is stark but beautiful. On the moon, you see grey plains stretching to a horizon much closer than on Earth, with mountains in the distance and the black sky above. Earth hangs in that sky, a blue and white jewel, painfully beautiful. On Mars, the landscape is red and rocky, with dust devils swirling in the distance and the salmon-colored sky overhead. The sun appears smaller and dimmer than on Earth. You move across the surface, completing your tasks. You collect samples, repair a solar panel, inspect equipment. Every movement is careful. A ripped suit could be fatal. You talk with your buddy constantly, checking on each other. Time passes differently outside. The work is exhausting, not just physically, but mentally. You must stay alert and focused. After a few hours, you return to the airlock. Inside, you remove your suit, inspect it for damage, clean off the dust that clings to everything. You are tired but satisfied. The mission was successful. Evening brings leisure time, precious hours when you can choose your activity. You might read a book, watch a video sent from Earth, play games with crewmates, or simply stare out a window at the landscape. Communication with family on Earth happens in this time too. On the Moon, it is almost real time, allowing actual conversations. On Mars, time delay means messages go back and forth asynchronously. You send a video message to your family, telling them about your day, then watch their latest message to you, sent hours or days ago. Dinner is the main social event. The crew eats together, discussing the day, planning tomorrow, sometimes arguing about trivial matters that take on exaggerated importance in the confined environment. But mostly, you appreciate each other's company. Humans need social connection, and your crewmates provide that. Before bed, you might spend time in the greenhouse, the most Earth-like space in the habitat. The smell of soil and plants, the green leaves, the gentle sound of water systems, all provide comfort. You tend your personal plant, a small tomato plant that you have nurtured since arriving. It connects you to Earth, to life, to growth and continuity. Finally, you return to your sleeping compartment. You secure yourself in bed, necessary in low gravity. The lights dim slowly. You might listen to music or nature sounds from Earth. Ocean waves, rain, birdsong. These sounds help you sleep, connecting you to the world you left behind. And you sleep, perchance to dream of Earth, of family, of the strange journey that brought you here, millions of miles from home, living a life that no previous human has lived, part of the first generation to truly reach beyond our planet and make a home among the stars. This is what life might be like. Not easy, but purposeful. Not comfortable by Earth standards, but tolerable and even rewarding. The challenges are significant, but humans are adaptable. We have lived in every environment Earth offers, from Arctic ice to tropical forests, from high mountains to ocean depths. We have proven our ability to survive and even thrive in hostile places. The Moon and Mars are simply the next frontiers. As space technology continues advancing, life off Earth will become progressively easier. Early settlers will have it hardest, with primitive facilities and constant danger. Later generations will inherit improved habitats, better equipment, and the accumulated knowledge of decades or centuries of experience. Eventually, children might be born in space or on Mars, knowing no other home. For them, Earth will be the distant, exotic place, seen only in pictures and stories. What would it be like to be one of those children, born on Mars and never visiting Earth? Your bones and muscles would develop in Martian gravity. Your body might be taller and more slender than Earth humans. You would be perfectly adapted to Martian conditions, but might struggle to visit Earth, where the gravity would feel crushing and overwhelming. You would grow up seeing Earth as a bright star in the night sky, knowing intellectually that billions of people live there, but unable to truly comprehend it. Mars would be your home, its red rocks and pink sky normal and familiar. You would learn about Earth's blue oceans and green forests with the same sense of wonder that Earth children feel about Mars. The relationship would be inverted. Your education would focus on skills needed for Mars life: engineering, agriculture, life support systems management. But you would also learn history, art, literature, philosophy. You would understand yourself as part of human civilization, connected across the light minutes of space to Earth and all its heritage. And perhaps you would dream of exploration yourself, not back to Earth, but forward to the asteroids, the outer moons, the depths of space. Each generation pushes a little farther. This is how settlement happens. Not in one dramatic leap, but in countless small steps across generations. The long-term future of humanity in space is hard to predict. We might establish ourselves throughout the solar system, with millions or billions of people living on multiple worlds and in numerous space habitats. We might eventually develop the technology to journey to other stars, carrying human consciousness and culture to distant planetary systems. Or we might remain primarily earthbound, with only small populations living off-world, finding that the challenges are too great or that Earth remains irresistibly attractive. What seems certain is that the effort will be made. Too many people dream of the stars for it to be otherwise. Too much momentum has already built in space programs, private companies, and public imagination. The question is not if, but when, and how quickly. There is also the question of what we will become in the process. Living in different environments might eventually lead to different varieties of humans, adapted to their specific worlds. Genetic engineering might accelerate this, allowing people to better tolerate radiation, low gravity, or other space conditions. We might merge with technology, becoming part biological and part machine, enhancing our capabilities to survive and thrive in environments our evolved bodies cannot handle. These possibilities raise profound questions about identity and humanity. If people born on Mars are genetically modified to thrive there, are they still human in the same sense? If someone's body is more machine than flesh, integrated with technology from birth, where is the boundary of personhood? These are not just science fiction questions. They are practical issues that space settlement will force us to address. Yet through all these changes, certain fundamental aspects of humanity would likely remain. We would still be conscious beings, capable of thought, feeling, and creativity. We would still seek meaning and purpose. We would still form relationships, build communities, create art and stories. We would still look at our surroundings and ask, what lies beyond? What is possible? These qualities have defined humanity throughout our existence. They would continue to define us among the stars. The story of humanity is, in many ways, the story of expansion and adaptation. Our ancestors left Africa tens of thousands of years ago, spreading across the planet. They encountered new environments, new challenges, and they adapted. They developed new tools, new social structures, new ways of thinking. They transformed themselves and the world around them. Space settlement is the next chapter in that story. It is more ambitious than anything we have attempted before, but it is fundamentally similar. We are moving into a new environment, one that requires new tools and new ways of living. We will adapt. We will transform the places we settle, and we will be transformed by them. And centuries from now, people looking back will see this era as the moment when humanity took its first steps toward becoming a spacefaring civilization. Let your mind drift now, floating among these possibilities. Imagine a future where your descendants might live on a dozen different worlds, each community adapted to its environment, yet connected by shared heritage and communication. Imagine children playing in low gravity, learning to fly with small wings attached to their arms, soaring through the interior of a vast space habitat. Imagine scientists on Europa drilling through kilometers of ice to reach the ocean below, seeking life in those dark waters. Imagine artists on Titan, creating sculptures from frozen methane, taking advantage of the unique properties of that strange, cold world. These images are speculative, dreams of what might be. Some will never come to pass. Others might happen in ways we cannot currently imagine. But they represent the aspirations, the drive to explore and settle that has characterized our species since the beginning. As you sink deeper into sleep, release any worry about whether these dreams will be realized. That is not for tonight. Tonight is simply for rest, for allowing your mind to wander through these possibilities without anxiety or pressure. The universe is vast and patient. Whatever humanity accomplishes will unfold in its own time. The question of whether humans can live beyond Earth has been answered, at least in principle. Yes, it is possible. The technology exists or is being developed. The locations are there, waiting. The will is present in thousands of people working toward this goal. All that remains is time, effort, and the countless small decisions that will determine how this future unfolds. But you need not solve these problems tonight. You need not plan the missions, design the habitats, or figure out the physics. Others are doing that work. Your task now is simply to rest, to let these ideas float gently through your consciousness like clouds across a sky, present but not demanding attention. Think of the night sky, that vast expanse of stars you have seen countless times. Each pinpoint of light is a sun, possibly with planets orbiting it. Some of those planets might harbor life. Some might be suitable for human settlement, if we can ever reach them. The universe is full of possibilities, an infinite frontier that humanity has barely begun to explore. You are part of this story, even if you never leave Earth. Your taxes might fund space agencies. Your children or their children might work in space industries. The technologies developed for space may improve your life on Earth. And simply by wondering about these possibilities, by being curious about what lies beyond, you contribute to the culture of exploration that makes space settlement possible. So, rest now. Dream of stars if you wish, or of nothing at all. Let your breathing slow, your muscles relax. Feel the weight of your body against the surface beneath you. A weight created by Earth's gravity, the same force that holds our planet in orbit around the Sun, that shaped the solar system, that governs the motion of galaxies. You are part of something vast and ancient and ongoing. The atoms in your body were forged in stars. Your consciousness is the universe aware of itself. And the dreams of space settlement that we have explored tonight are the universe imagining new ways to organize matter, to spread awareness, to create beauty and meaning in the vast expanse. All of this will continue tomorrow, and the next day, and the days after. The work of space exploration and settlement proceeds in small steps, each building on the last. Robots explore distant worlds. Engineers test new technologies. Scientists analyze data and propose theories. Astronauts train for future missions. And slowly, steadily, humanity extends its reach. But tonight, that work continues without you. Others carry it forward while you rest. And that is as it should be. We are not meant to solve everything at once, to carry all burdens ourselves. We are part of a larger whole, a civilization that accomplishes great things through the combined efforts of millions of people across generations. Your part in this story is to live your life, to be curious, to care about the future. And right now, to rest, to let your body recover from the day's activities, to let your mind process and integrate experiences, to sleep, that mysterious state where consciousness dims and the brain performs its nightly maintenance. As you drift away now, remember that the universe is patient. The stars have burned for billions of years and will burn for billions more. The planets will continue their orbits. The possibilities for human expansion into space will remain, waiting for us to be ready. There is no rush. There is only the steady, patient work of progress, one small step at a time. And tonight, your step is to rest well, to sleep deeply, to let these dreams and possibilities fade into the gentle darkness of sleep. The moon rises over Mars in an image captured by a future rover. Earth shines like a bright star in the Martian sky. Astronauts in a lunar habitat watch Earth rise over the moon's horizon. A child born in a space habitat looks out the window at the planet where their grandparents were born. These scenes play out in your imagination, gentle and distant, requiring nothing from you but passive awareness. And now, even that awareness fades. The images become less distinct, less important. Your breathing has slowed to a peaceful rhythm. Your body is deeply relaxed. The concerns of the day have released their hold on your mind. You have done enough for today. You have wondered about the universe, contemplated humanity's future, engaged with ideas that span centuries and light years. That is more than enough. Now you simply exist, in this moment, in this comfortable place, with nothing required of you except to be. Let the stars fade, let the planets dim. Let the grand story of human expansion into space become a distant background, unimportant for now. What matters is this moment, this breath, this perfect relaxation. The universe holds its possibilities patiently, waiting. The future will unfold as it will, and you, having explored these ideas, having asked these questions, having imagined these possibilities, can now release them all and let yourself settle into the peaceful darkness of sleep. Picture yourself floating in space. Not the cold vacuum, but a warm, gentle nothingness. You are weightless, supported by invisible forces. There is no up or down, no left or right. There is only this floating sensation, this perfect suspension where your body feels lighter than air, free from all the usual tensions and pressures. You float in this comfortable darkness, safe and serene. Around you, far in the distance, stars twinkle softly. They are not harsh or demanding. They do not require your attention. They simply exist, like night lights placed throughout infinity, providing just enough illumination to remind you that you are not alone. The universe is populated with these distant suns, each perhaps with its own family of planets, its own story being written across billions of years. But you need not think about those stories now. You need only float here, in this perfect state between waking and sleeping, where the boundaries of your body become less distinct, where you cannot quite tell where you end and the universe begins. Perhaps this is what astronauts feel when they look out the window of their spacecraft and see Earth floating in the void. Perhaps this is the overview effect, the profound sense of connection to everything, the understanding that we are all part of one cosmic whole. You are stardust, quite literally. The calcium in your bones was created in the heart of a dying star. The iron in your blood was forged in a supernova explosion. The oxygen you breathe with each slow, peaceful breath was produced by stars burning through their fuel over billions of years. You are not separate from the cosmos. You are an intrinsic part of it, a way for the universe to experience itself from the inside. This connection persists, whether you think about it or not, whether you are awake or asleep, whether you are on Earth or someday perhaps on another world. The atoms that make up your body have existed for billions of years and will continue to exist for billions more, though not always in this particular arrangement. You are a temporary pattern, a beautiful and complex organization of matter that can think and feel and wonder. And when this pattern eventually dissolves, as all patterns must, the atoms will go on to form new patterns, new arrangements, continuing the endless dance of transformation that characterizes the universe. But that is far in the future, so far that it need not concern you now. Right now, you are here, you are alive, you are conscious and breathing and existing in this particular moment. And that is remarkable enough. That is miracle enough, if we use that word to mean something rare and wonderful rather than supernatural. Feel your connection to Earth beneath you. Even if you are many floors up in a tall building, even if there are layers of concrete and steel between you and the ground, you are still connected to this planet. Earth's gravity holds you gently, just enough to keep you from floating away, but not so much that you feel crushed. The air around you came from Earth's atmosphere, cycled through countless lungs and leaves before reaching yours. The water in your body was once rain, once ocean, once ice, cycling endlessly through the water cycle that has sustained life for billions of years. You are part of Earth's living system, connected to every other living thing through shared biochemistry, shared history, shared dependence on this one precious planet. And yet, you are also part of something larger, connected to the entire cosmos through the fundamental forces and particles that make up everything. You exist at the intersection of the local and the universal, the temporary and the eternal, the individual and the collective. These philosophical thoughts need not keep you awake. Let them wash over you like gentle waves, acknowledged but not demanding focused attention. You can be aware of your cosmic nature without needing to fully understand or analyze it. Some truths are better felt than thought, better experienced than explained. Your eyelids are heavy now, or perhaps already closed. Your breath flows in and out without effort, automatic and rhythmic as the tides. Your heartbeat continues its steady pulse, that remarkable organ that has been beating since before you were born, and will continue until your story reaches its natural end, whenever that may be. But that too is far away. Right now, your heart beats strongly and surely, circulating oxygenated hemoglobin to every cell, sustaining the complex orchestration of processes that constitute life. You can feel the pulse if you pay attention to it, but you need not pay attention. Your body knows what to do. It has been doing this for your entire life without conscious direction. Trust it to continue. Trust the ancient wisdom encoded in your DNA, the product of billions of years of evolution, countless generations of ancestors who survived long enough to reproduce, passing forward this precious genetic information that became you. And now, that body that carries you through each day needs rest. It needs this time of reduced consciousness, this period when it can redirect energy away from active movement and thought toward maintenance and repair. Cells throughout your body are being replaced, damage being corrected, memories being consolidated, waste products being cleared away. All of this happens automatically while you sleep, orchestrated by systems that arose through evolution and refined over millions of years. You need only allow it to happen. You need only stop trying to control everything and simply be. This is harder than it sounds in our modern world, where we are taught to be productive, to be active, to be constantly doing something. But sleep is not doing. Sleep is being. It is the most fundamental form of self-care, the biological necessity that cannot be permanently postponed or replaced with any substitute. So give yourself permission to sleep. Give yourself permission to let go of the day's worries and tomorrow's responsibilities. They will still be there in the morning, and you will be better equipped to handle them after sleeping well. The problems that seem insurmountable when you are tired become manageable after rest. The challenges that trigger anxiety when you are exhausted become opportunities when you are refreshed. Sleep is not weakness or laziness or wasted time. It is biological necessity, evolutionary wisdom, essential maintenance. Every living creature that has a nervous system of any complexity needs sleep or something analogous to it. Your cat knows this instinctively, sleeping for most of the day without guilt or worry. Birds sleep, reptiles sleep, even insects have sleep-like states. You are following an ancient pattern, older than humanity, older than mammals, older than any modern animal group. So sleep now, knowing that you are doing exactly what you should be doing, what your body needs you to do, what evolution has programmed into every cell. Sleep without guilt, without anxiety, without planning or worrying or trying to solve problems. All of that can wait for tomorrow. Tonight is for rest. The visions of lunar bases and Martian settlements fade now, becoming less than dreams, less than memories, simply possibilities that exist somewhere in the space of all possible futures. They may come to pass, or they may not. They may look exactly as described or completely different. It does not matter right now. What matters is this moment, this breath, this steady descent into sleep. Your mind grows quieter with each breath. The internal dialogue that usually narrates your experience begins to fragment and fade. Thoughts become less coherent, more dreamlike. This is normal and natural. This is the transition from waking consciousness to sleep consciousness, from the beta waves of active thought to the alpha waves, relaxation to the theta waves of light sleep, and eventually to the delta waves of deep sleep. Let it happen. Do not fight it. Do not try to maintain alertness or awareness. Simply allow consciousness to dim, like a light on a dimmer switch, gradually, smoothly, until finally it flickers out and you enter the realm of dreams. And in that realm, you are free. Free from the constraints of physics, free from the limitations of your body, free from the worries and responsibilities of waking life. You might fly. You might visit impossible places. You might meet people who do not exist, or who exist only in memory. You might experience emotions intensified beyond what waking life provides. Or you might experience nothing at all, or at least nothing you remember upon waking. All of this is fine. All of this is natural. There is no right way to dream, no wrong way to sleep. Your brain knows what it needs to do, and it will do it, whether you remember the experience or not. Many of your dreams you will forget within moments of waking. Some you might remember vividly for years. The remembered dreams are no more important or meaningful than the forgotten ones. They are all part of the same process, the same nightly journey into the unconscious. So dream freely now, or do not dream at all. Sleep lightly, or sleep deeply. Wake briefly in the night, or sleep straight through until morning. However your sleep unfolds tonight is exactly how it should unfold. Trust the process. Trust your body. Trust that when morning comes, you will wake refreshed and restored, ready to face whatever the new day brings. The stars still burn in the darkness, but you no longer see them. Earth continues its rotation, but you no longer feel it. The moon orbits overhead. Mars follows its distant path. The solar system spins through the galaxy, and the galaxy wheels through the universe. All of this continues, whether you are aware of it or not, independent of your consciousness, governed by physical laws that operated for billions of years before you existed, and will continue for billions of years after. But right now, in this moment, you exist. You are here. You are alive. You are sleeping, or about to sleep, engaged in the nightly ritual that sustains all complex life. And that is beautiful. That is enough. That is everything. Sleep well. Dream freely. Know that tomorrow the stars will still be there, quietly inviting humanity to reach for them, in no hurry, content to wait for as long as it takes. The universe is patient. The possibilities are endless. And you, having wondered about them for this brief time, can now rest, secure in the knowledge that the work continues, the dream persists, and the future awaits. Good night.